My name is PHANG. My message number is 2025999. Today, our group will talk about the auto brightness LED-based lamp control. This is my team member and their matrix number. Now I will discuss about the introduction. The automated brightness lamp, as the name implies, is used to switch on and off the lamp without the need for human interaction. It detects the strength of light in its surroundings and determines whether it is dark or bright, and it turns on automatically when the surroundings are dark and turn off when it gets lights from the surroundings. The light intensity is detected using an LDR sensor. The auto brightness lamp reduces brightness in light area and increase brightness in dark areas. The auto brightness lamp and LDR are used to detect the motion and brightness. The mini project has been conducted through the buck converter circuit and the LED controller circuit. Based on the LED controller circuit, the components used were LED, root, display, Arduino UNO, and LDR. The light bender resistor is an important component in this circuit. It is a sensor which is a type of resistor whose resistance reduces when it is exposed to light. In contrast, it has a high level of resistance in the dark. The temperature of the filament also will increase as the resistance increase. When the temperature of the filament increases to the maximum temperature that the lamp can accept, the lamp will light up easily. This is due to the filament being burned in order to light the lamp.
In order to achieve uniform brightness, simple voltage control is not enough. Therefore, it is necessary to consider two non-linear relationships. The first one is IF, where IF is the LED forward current equals to K1 times the supply voltage Vs. The second one is the luminous flux phi equals to K2 times the LED forward current IF. The above relationships describe the dependence between LED supply voltage Vs and its luminous flux phi. Therefore, it can be said that the practical realization of LED driving circuit with automated dimming ability depends on the assumed rule of LED luminous control. Two commonly used methods found in various literatures of LED luminous control are amplitude modulation and pulse width modulation. As each of these methods has its own benefits and setbacks, it is essential to identify the critical characteristics for each application before implementing the auto brightness technology using these two methods. The first method of auto brightness control is known as the amplitude modulation. By using this method, the LED's current waveform is adjusted cycle by cycle to achieve the desired level of luminous flux. This is done by using a simple potentiometer or a current regulator circuit and thereby increasing or decreasing the output luminous flux. The LED current is regulated by a control architecture by simply adjusting the reference value of the current feedback as shown in the figure above. Resistor Rs in the circuit above is used to sense the voltage and subsequently to measure the LED current. This measured LED current is then used by a controller to adjust the output voltage and the current of the DC to DC converter. One of the benefits of this method is it provides a simple and cost-effective dimming solution to a single LED-based lamp device. However, it may not be able to deliver the best overall performance for an array of LED-based lamps. This is because it leads to chromaticity shift as the drive current value varies due to variation in the characteristics of different LEDs. Based on our research done earlier, we know that the output of the luminous flux and the chromaticity depends on the drive current. This knowledge is essential in order to apply the second method in our auto brightness lamp. As stated earlier, a small change in LED drive current may cause a significant chromaticity shift, particularly in an array configuration of LEDs. Hence, in order to maintain the required chromaticity, constant current is necessary to drive the system. As a solution, the pulse width modulation (PWM) provides the most convenient method for LED luminance control without altering the current. The system regulates the output current by changing the duty cycle, in other words, varying the pulse width using the formula above, D equals to T on divided by Ts. Therefore, it can be stated that the effective brightness B effective of the LED-based lamps under the pulse width modulation (PWM) control follows the output current I/O, substituted by BO, which is the LED brightness obtained at continuous current.
My name is Dineswaran Murugan and my matrix number is 202600. So now I'll be talking about our mini projects methodology. For mini project, we have developed a buck converter circuit and LED controller circuit, which consists of Arduino microcontroller. We use Proteus software in order to build our circuits and simulate them to obtain the input and output graphs together with the results on the LED. For buck converter circuit, we use PWM for MOSFET to control the output voltage. The type of MOSFET used was IRF6215. For the LED controller circuit, we use light dependent resistor LDR in order to sense the amount of light present. All the simulation was done as per procedure and the results were recorded below as waveform and calculation in the discussion part. Now, I'll be talking about the working principle of buck converter circuit. Based on the figure, the working principle of a buck converter can be branched into few steps. First, when the switch turns on and lets the current to flow to the output capacitor and charge the capacitor. Since the voltage across the capacitor cannot rise instantly, and since the inductor limits the charging current, the voltage across the capacitor during the switching signal is not the full voltage of the power source. Next, the switch now turns off. Since the current in an inductor cannot change suddenly, the inductor creates a voltage across it. These are the components used for buck converter circuit. First is the voltage source. A voltage source provides a constant 12-volt DC voltage. Next is the MOSFET. MOSFET is a device that improves efficiency at higher switching frequencies and light loads. By considering a 12-volt is converted to 5-volt, we can see a smaller duty cycle, hence less RMS current. The high side and the more the low side MOSFET needs to handle. Next is the diode. Here, the diode blocks any reverse inductor current flow and the voltage across the inductor goes to zero. Next is the inductor. Inductor provides a stable and continuous current to the load as the PWM signal switches. The fifth component used here is the capacitors. Capacitors functions as a smoothing device which helps to reduce the ripple voltage and smoothens the output voltage. Moreover, the capacitor also functions as a device which stores electrical energy in an electrical field and discharges then when needed. It is a passive electronic component with two terminals. Next is the resistors. Resistors function as to reduce the reactive current that passes to the feedback resistance, hence improve the efficiency. The last is the digital voltmeter to display the output voltage. The circuit diagram for LED controller circuit is shown below, and the pins connected to the Arduino is also listed below. First is the VCC. VCC is also known as Voltage Common Controller, is the power input of a device. In this project, 5-volt which was converted from the buck controller circuit will be connected to the Arduino VCC input pin. Next is the ground pin. Ground pins are used to close the electrical circuit and provide a common logic reference level throughout the circuit. Next is the A0 pin. The A0 pin acts as the input and the pin 9 acts as the output. Thank you.
Hello, my name is SYAMSUL with ROSNI with matter number 202463. Now I'm going to present about the simulation and result for our project. Okay, this is the buck converter circuit for our project. This circuit can step down the 12-volt battery to the 5-volt. To get that, we use the MOSFET and we control the gate input of the MOSFET. We do cycle about 55%. So after I run it, as you can see here in this voltmeter, it actually shown the output for the circuit at 5 or 4.99 volt. So with this voltage, we supply the main circuit. Okay, now this is our main circuit. This for the supply from the buck converter circuit. As you can see, the voltage is about 5 volt. Same with the output we get for our buck converter circuit. Now this is a LDR sensor. This is used to read the reading of the light that in the area. This is our LED, and this oscilloscope is used to read the duty cycle that produce the PWM signal that produce in pin 9. Okay, we use Arduino for our main brain of the project, and the coding is here. Okay, first the ADR sensor we introduce as an integer and we define it as 0 for the initial condition. Here for setup, for input we use a pin number A0 and output pin number 9, and so begin is for the Arduino to communicate. Okay, this is our main function. Okay, first the sensor value will, as you can see here, the sensor value A0 will read the analog value that received from the ADR. Next, after it received, we print the value that it received from the ADR to the board, and after that we write the value to the output number 9 and map it as if the reading is it detect the high value, so we put the lamp in turn off condition. After it read at the highest value, at the low value, we put it at the high at the turn on condition at the full brightness. So the delay for this we use for 500 milliseconds. Okay, now let's run it. Okay, as you can see, if the ADR did not detect any light from this lamp, so our LED will turn on with full brightness. Wait, I turn on. Okay. As you can see here, the PWM output that produced at pin 9 will near 100. Also, we can call it full brightness for the LED. After we turn on the lamp at this and the ADR detect the light, as you can see here, the low part is slightly increased than before. And until we near it, as you can see here, the lamp brightness will go dim, and also the PWM at oscilloscope, the low part will go bigger. And if we go the maximum distance that this lamp can go near to the ADR, the LED green will turn off. And for the oscilloscope part, as you can see here, the lower part is near 100. It's the inverse from before. So that's all for our project. Thank you very much.
Now we will go to the last part, which is the conclusion. In conclusion, the buck converter circuit and the LED controller circuit of the outdoor brightness lamp have been successfully designed. The outdoor brightness lamp mechanically and function has been discussed. The association between the brightness of the surrounding and the outdoor brightness lamp on-off has been discovered. The buck converter is used in the buck converter circuit to step down the supply from the 12-watt battery to the 5-watt. The capacitors move the input and ensure that all the input current is changed. The duty circle has utilized to decrease the voltage from 12 watt to 5 watt. The buck converter is a power converter that steps down voltage while lowering less average current from its power supply to its output supply, depending on the output filter design utilized. When a buck regulator power at LED, the LED commonly conduct the AC output ripple current in addition to the DC current. The ripple current content causes an increase in LED power dissipation, which is measured. When the LDR detects no lights from the torch, the resistor will increase the temperature of filament increase. The LED lights fully and the oscilloscope will show the duty circle for PWM. When the torch is turned on and close to an LDR, the resistor will decrease, the temperature of the filament decrease. The LDR brightness will gradually reduce, switch off if the LDR is extremely close to the torch. It is because the filament is burned to light up the lamp. This demonstrates how the brightness of the outdoor brightness lamp is changed by the brightness of the surrounding. The resistance will affect the brightness of lamp by changing the temperature of filament in the lamp. The oscilloscope were used to analyze the circuit results. In summary, this demonstrates that the project has completed effectively and that it may be expanded in the future. Thanks for watching.